Will light be bent by the gravitational field? A very well-known corollary of the special theory of relativity is, mass and energy are equivalent. This is summarized in Einstein's famous equation E equals mc squared. E is energy, m is the mass, and c is the speed of light. Albert Einstein pointed out that an object can never actually reach the speed of light, because then its mass will be infinite. So, the theory of relativity limits the speed at which an object moves, i.e. waves other than light or without intrinsic mass. No other normal object can exceed the speed of light. It can only move at speeds equal to or below the speed of light. Such is the theory of relativity and Newton's theory. An irreconcilable contradiction arises. We know that Newton's theory states that objects are attracted to each other. The magnitude of the attraction depends on the distance between them. This means that if we move one of the objects, then the attraction of the other object will change immediately. Let's take the example of the sun. Suppose the sun is gone. Well, according to Newton's theory, the earth will immediately perceive the sun. The attraction ceases to exist and goes off the rails. At this point, the gravitational effect of the sun's disappearance will reach us at infinite speed, and not at or below the speed of light, as special relativity requires. From 1908 to 1914, Albert Einstein was looking for a way to reconcile theories of special relativity and gravitational theory. 1915, after nearly a decade of reflection and research, he finally came up with the general theory of relativity. This allows the special theory of relativity and the theory of gravity to be reconciled with each other. Einstein and the general theory of relativity. A revolutionary idea was proposed. That is, gravity is not a force in a flat spacetime as we previously thought. Rather, it is the result of the fact that time and space are uneven. General relativity proposes the distribution of mass and energy in spacetime, causes spacetime to bend or warp. Objects like the Earth are not called. Gravitational force acts while moving along the orbit. Rather, it moves east-west along the curved track closest to a straight path. This thing is called geodesics. A geodesic is the shortest, or longest, path between two adjacent points. For example, the surface of the Earth is a curved two-dimensional space. The geodesic line on Earth is called a great circle, and the equator is a great circle. In the general theory of relativity, although objects always walk in a straight line in four-dimensional space, but in three-dimensional space, it still follows a curved path. Take, for example, an airplane flying over a mountainous terrain. It is flying in a straight line along the three-dimensional space, but it's a shadow on the two-dimensional ground. But it follows a curve. From this we know, it is in this way that the mass of the sun bends spacetime, so that in the four-dimensional spacetime the Earth moves along a straight path. It seems to us that it is along a three-dimensional space, runs in an elliptical orbit. At this point the general theory of relativity and Newton's predictions of gravity are almost identical. They all accurately describe the orbits of the planets. But then people found some planets and what Newton's theory predicted. The orbital deviation is very much in line with the general theory of relativity. This verifies the correctness of the general theory of relativity. The fact that spacetime is curved means light doesn't walk in a straight line as it might seem in space. In fact, light rays must also follow geodesics in spacetime. That is, general relativity predicts that light will be bent by the gravitational field. According to this prophecy, because of the mass of the sun, the path of light near the sun will bend slightly. This means that the light from a distant star is there. Makes it seem to the observer on Earth. The star appears in different positions. 1919, a British expedition observed a solar eclipse from West Africa. It proves that light is indeed deflected by the sun, as predicted by the theory. As a result, people have become more affirmative of the correctness of the general theory of relativity.